And I'm Mac.
For our project, we chose to describe the control system of a typical arcade claw machine, which can be described as a discrete system and a 3D pendulum. Claw machines have a pretty standard joystick for users to input commands into the system, as seen here. These inputs direct the crane along two tracks, one horizontal and one vertical, as seen here in the video. You can note that when the crane stops, it oscillates, and this is where we do most of our analysis.
To analyze our system, we made the following assumptions. A few to point out are that we treated the claw as a mass on a weightless string and that the claw behaves like a three-dimensional pendulum. This is a free body diagram of the claw itself at a moment in time when the user stops inputting the commands into the system. We have the center of gravity at a distance L away from the top of the claw. As a result of the claw's initial velocity, there is a moment about an axis coming out of the screen. In order to describe the position of the claw, a polar axis coordinate system can be adapted.
To describe a 3D pendulum using polar coordinates, we can use two variables. Theta is a positive angle from the x-axis in the direction of the y-axis, and psi is defined positively from the mass to the xy plane, or negatively from the xy plane to the mass.
Our total energy is the sum of the current kinetic and potential energy. This can be defined in our polar coordinates as shown. We can define our state vector in terms of psi and theta, which yields a state equation of psi dot and theta dot. Our derivation for psi dot and theta dot is shown. You can pause the video for a better look.
If we set psi dot and theta dot equal to 0, we can solve for our equilibrium point. Here, when psi dot equals 0, it simplifies down to cosine psi equals 0, which yields that psi must equal plus or minus pi over 2. Likewise, for theta dot equals 0, this equation simplifies down to 1 divided by tan psi times sine psi. When we take the limit, pi over 2 satisfies this equation. Therefore, psi must equal plus or minus pi over 2 at equilibrium. Unlike typical equilibrium points, we don't present the solution as a vector because, at phi equals pi over 2, theta does not exist in our polar coordinate system. The claw being stable at the bottom is represented entirely by the phi equals negative pi over 2 value. Here's another crane from the same arcade. We analyzed this crane, and here we see the amount of time that it took to get a steady state, which we calculated to be 6.4 seconds. Likewise, we slowed it down and found the rise time to be 167 milliseconds.
In Simulink, we used an impulse block to model the initial moment that the claw experiences. We then used a PID block that would model our dampening forces, such as friction and air resistance, and modified it so that it could meet our rise time and settling time that we found earlier.
With this claw, the dangling coil that supplies power causes the claw to rotate as it lowers. This becomes very difficult to describe since the three-dimensional force, the angular acceleration, and the distance x from the top of the machine are all changing simultaneously and depend upon the claw's frictional components and internals. If we define the claw's position when it is at the top of the machine as theta equals 0, we can infer that if there was nothing to stop its rotation, the claw would stabilize 180 degrees later on the side where the coil is connected to the machine. And that's it for our video.
Oh my god!